We're surrounded by concrete every single day. Our buildings, our bridges. We tend to think of it as just, this solid gray stuff that's just there. But underneath that simple surface, there's a hidden world of incredible forces, really clever design, and a constant slow-motion battle against failure. Today, we're going to pull back the curtain on the genius of how we design these structures to keep us all safe. But first, here's a question for you, a real puzzle. How can the dome of the Pantheon in Rome, which is almost 2,000 years old, still be standing while a lot of our modern engineering marvels are designed for a much, much shorter lifespan? It just doesn't seem to add up, right? Well, to get to the bottom of that, we have to start with a paradox at the very heart of this story. Yep, we're talking about concrete's ancient paradox. I mean, think about that for a second. The Pantheon, built with this ancient type of concrete, is still in amazing shape, but our modern structures, built with all our advanced science, often have a design life of maybe a century or two. It feels totally backwards, doesn't it? Well, the secret isn't about what the Romans had, it's about what they didn't have. And what they didn't have was this, the incredible alliance of concrete and steel that literally builds our entire modern world.
Okay, so let's break this down. Concrete is an absolute beast when you squeeze it, what we call compression. Think of a giant pillar holding up a roof. It's incredibly strong. But try to pull it apart, put it in tension, and it's super weak. It just cracks. Now, steel is the complete opposite. It's amazing in tension. Think of the cables on a suspension bridge. So what do you think engineers did? They put them together.
We stick steel bars, or rebar, right inside the concrete. The concrete handles all the squeezing, and the steel inside handles all the pulling. It's a perfect team-up, right? A construction superhero duo. And this material, reinforced concrete, is everywhere. But here's the twist. This perfect partnership has a fatal flaw baked right in. So, knowing this vulnerability existed from the get-go, engineers had to get really, really clever. They came up with the whole philosophy for designing against failure. It's called limit state design, and the idea is actually pretty elegant. Instead of just designing something to work, you basically think of all the different ways it could possibly fail or stop being useful. Those are the limit states, and the whole goal is to design the things that the chances of it ever reaching one of those states are practically zero. So, the first and most important category is the ultimate limit state, or ULS. This is the big one. This is the stuff of nightmares. We're talking about total collapse, foundations giving away, anything that could lead to catastrophe. The entire design is laser-focused on staying as far away from this point as humanly possible. Then you've got the other side of the coin, the serviceability limit state, or SLS. This is less about, is it going to fall down, and more about, can we actually use this thing comfortably? Are there giant, scary-looking cracks? Does the floor feel like a trampoline when you walk across it? If a bridge sags so much it spooks drivers, it's not really doing its job, even if it's technically safe. And this quote just nails the difference, doesn't it? The ultimate limit state, that's the chain's weakest link. If that one link snaps, it's all over. But the serviceability limit state is like the total stretch of the entire chain. It's about the performance of the whole system. And engineers have to design to prevent both. So how do they actually do it? Well, they play this really smart, really important game with the numbers to build in this massive safety cushion from the very start. The core idea is simple, but it's brilliant. You basically become a professional pessimist. You do two things. First, you pretend that all the loads and forces, the actions, are going to be way bigger than they'll ever really be. And second, you pretend that the materials you're using, the resistance, are way weaker than they actually are. It's a fantastic double-sided safety net. Okay, let's make this real. Let's say we have some concrete, and we test it in the lab. We find out its real-world strength is 30 megapascals, or MPa. Don't worry about the unit, just think of 30 as its true strength score. But when it comes time to do the safety calculations, you are absolutely not allowed to use the number 30. No way. For safety's sake, you have to pretend it's weaker. So for our design, that 30 MPa concrete, its new score is just 20 MPa. Boom. Right there, we've built in a huge safety margin just by deliberately underestimating what it can do. And this whole safety-first approach gets applied to everything using what are called partial safety factors. You'll notice the factor for concrete is higher than for steel. Why? Well, because making concrete is just more variable, so we build in a bigger buffer. Then we do the same thing for the loads. We pretend the building's own weight is 35% heavier, and that things like people or snow are 50% heavier than we ever expect them to be. It's safety on top of safety. Okay, so this brings us all the way back around. If we have this incredibly robust safety system, why don't our structures last forever, like the Pantheon? What is that fatal flaw we mentioned? And here it is. The Pantheon's secret weapon wasn't a special ingredient. It was a missing ingredient. It has no steel. The very thing that gives modern concrete its amazing strength, that steel rebar is also its Achilles heel. Because steel can do something that the Pantheon's concrete can't. It can rust. And here's how this internal attack happens. See, at first, the steel is pretty happy inside the concrete, which creates a natural protective chemical shield around it. But over time, things from the outside environment start to sneak in and break down that shield. Once the steel is exposed, it starts to rust. And here's the killer part. Rust takes up way more space than the original steel. This expansion creates this massive internal pressure that literally blows the concrete apart from the inside out. It's an enemy from within. And what triggers this? Just everyday stuff. The carbon dioxide in the air we breathe, the salt we put on our roads and bridges every winter, even that nice, salty air at the beach. These are the agents that are constantly trying to get inside and start that destructive chemical reaction. So, the next time you look at a concrete building or a bridge, try not to see it as just a static, boring object. See it for what it truly is, a dynamic system, brilliantly engineered to handle massive forces, but at the same time, locked in this constant, silent, slow-motion battle with the chemistry of decay. The fact that our structures stand for as long as they do is honestly a testament to incredible engineering. And it kind of makes you wonder, doesn't it? What other invisible forces, what other hidden genius is holding up the world all around you right now?